Hello everyone, welcome back for another lesson. In this lesson, we will be looking at balancing equations. Before we begin balancing equations, we need to make sure that we all speak the same language. So here you have a few expressions that I may have been using, but that you will hear often enough in the future. So first we have, let me start in the middle here, the subscript. So when I look at my molecule is O2. What this means is that there are two atoms of oxygen that are bonded together. So the subscript tells me how many atoms of this element are present within the molecule. So this is called a subscript. My O2 is in the gas form. It says G in brackets. So this is the state of matter. And in front, I have a number 2. So that's called a coefficient. So that means I have two molecules of O2. If I was to draw this, I would have O double bond O. So that's one molecule, it's in the gas form, and I would have a second molecule in the gas form as well. So this is the information provided within this whole expression. Okay, so two molecules of O2, both of which are in the gas form. So now that we all speak the same language, we can move on to balancing equations. So the law of conservation of matter says that nothing is created, nothing is destroyed, everything is transformed. So that means whatever atoms we had at the beginning of the chemical reaction will still be present at the end of the reaction, but they will have been rearranged. New bonds are formed. Now, in order to follow that rule, to respect that rule, we have to make sure that the numbers of atoms are equivalent on both sides. So if we look at the following examples, or example I should say, sorry. I have N2 that reacts with H2 to form NH3. Now if I count the number of each type of atom on each side, I have 2 nitrogens, 2 hydrogens, right? Because it says 2N and 2H. And on the other side, I have NH3. So I have 1 nitrogen and 3 hydrogens. Now clearly, these numbers are not the same. I started with 2 nitrogens, I ended up with 1. Where did the other one go? And for hydrogen, there's one that appeared out of thin air. That's not possible. In nature, that is not what we observe. In nature, when these reactions occur, the number of atoms at the end is the same that the number of, let me rephrase this. The number of atoms that I count at the end of the reaction is the same as the number of atoms that there was at the beginning of the reaction. Nothing is created, nothing is destroyed, everything is just transformed or rearranged. Okay, so this doesn't work. There's something off here. So that means I must have more than one molecule of N2 and or more than one molecule of H2 and or more than one molecule of NH3 present in this whole system, in this whole reaction. Now, how do we figure out how much of what there was or there is at the end? Well, we have to add the coefficients in front. So when we balance an equation, we are only allowed to put numbers in front, to change the coefficients. We're not allowed to change either the substances. So I can't say I'm going to replace N2 by something else. That's not what's observed in nature, in reality. This is the actual reaction. This substance reacts with this substance and creates this substance. There's no ifs and buts about that. That's the way it happens. So because of that, I cannot change the substance, nor can I change the subscript, sorry. So I'm not allowed to change the subscript. I'm not allowed to change the atoms either. Okay, the only thing I can change is the coefficient in front. Now you're going to say, how did I come up with these numbers? There's different ways of doing it. I will walk you through the process in a moment. But just to show you how this works once it's done, well, I have N2. So 2 N's times a coefficient of 1. So 2 times 1 gives me 2. For hydrogen, I have 2 hydrogens times 3. Right? Because I have 3 molecules of H2. So 3 times 2 H's gives me 6 H's. Now if I compare this to the other side, I have 1 nitrogen times 2. That gives me 2 nitrogens. And I have 3 hydrogens times 2. That gives me 6 hydrogens. You have to see the coefficient as basically something that multiplies the whole molecule. So it's as if you put brackets like this. So it's 2 times N and 2 times 3 H's. So you distribute like you would do in math. Now, if I compare my numbers, I have 2 nitrogens on the reactant side, and I have 2 nitrogens in total on the product side, 6 hydrogens on the reactant side, 6 hydrogens on the product side. Okay, so we can only use whole numbers, never fractions, and I'll show you if you have a fraction what to do with that. And you have to try and simplify your coefficients as much as possible. Again, I will show you an example as to where you would need to do that. It's a little bit like when you do a recipe, they'll give you the basic measurements. Now, if you wanted to double or triple or quadruple the recipe, you could, but they always give you the simplest version of the recipe. So think of this as a recipe. You want to express it in its simplest version. That is why you want to use the smallest possible coefficients. Okay, and again, I will show you an example of this. How does this apply? Now, when you balance, I will show you how to go about it, but just keep in mind you want to balance the hydrogens and the oxygens last, because as you will see in the following examples, sometimes they're present in more than one of the substances, so it makes it a little bit more complicated to balance. And also, if you have polyatomic ions present, start with those. You'll see it makes your life a little bit simpler. Again, I will show you an example. So let's take a look at examples. Okay, so we'll take them one at a time. Let me just extend my page, sorry. Okay. So if I look here, what should I start with? I said do not start with oxygen or hydrogen because, as you can see, they can be present in several places. So I have hydrogen and hydrogen and hydrogen. So it's in 3 out of 4 molecules. So that makes it a little bit more complicated. Try to start with the atoms that are there only once on each side. So for example, sodium and sodium, or chlorine and chlorine. So let's say I start with sodium, and you don't have to necessarily start with the first substance on the left-hand side. You can start with any. Okay, so but let's say I start with sodium. So I have 1 sodium and 1 sodium. Those numbers are already equal. I don't need to multiply either side by anything. Okay, then let me take a look at chlorine. 1 chlorine, 1 chlorine. Oh, that's great. It's already equal. Okay. Moving on, I only have hydrogen and oxygen left. Which one should I do first? Well, I would choose oxygen for the simple reason that I have oxygen only in 1 molecule on this side and only in 1 molecule on this side. That's going to make it simpler to balance. So 1 oxygen and 1 oxygen. Ooh, that's already equal. Perfect. Hydrogens, I have 1 and 1. So I have 2 in total on this side, and I have 2 in total on this side. So this is also already balanced. So this was a trick one in a sense. It's already balanced. Okay, it is already in its simplest version, but it was just to walk you through the motions. So this, I could put the coefficients of 1 in front. You don't have to. It's not incorrect to put it, but we normally don't put the 1s in front. So you could have left it as is or put the 1s. Okay, moving on to the next one. Zinc, hydrogen, chlorine. So hydrogen will do last. Let's start with zinc. 1 zinc, 1 zinc. That's already equal. Great. 1 chlorine, 2 chlorine. So since I have 2 over here, I need to make it equal over here. Am I allowed to put a 2 as a subscript? No, I said I'm not allowed to change the molecule itself. If I put a 2 over here, well, that's going to change the molecule. It's not HCl anymore, it's HCl2. So I'm not allowed to do this. This is not the same molecule as before. So instead, I'm going to put a 2 in front. I'm only allowed to change the coefficient. So I have 2 times HCl. So 2 times 1 gives me 2 chlorines. And I have 2 chlorines over here. So that one is already balanced. And I already did my zinc. I said I'm going to keep it as 1 zinc and 1 zinc. That works. So now I know that the only thing I have left to balance, the only coefficient I haven't looked at is this one for hydrogen. So I have 2 times 1 is 2 hydrogens, and I already have 2 hydrogens over here, so that means I don't need to touch it. I keep it as 1 and everything is balanced. Okay, next. I have here a combustion. So we will look at the types of equations down the road. So disregard the fact that I said it's a combustion. It's not important. All right, so back to what we were doing, balancing. So 1 carbon, 1 carbon. Wonderful. Let me take here 1 and 1. They're already balanced. Now I'm already at the oxygens and the hydrogens. So oxygen, oxygen, oxygen. Let me not do that one right away. I'll do the hydrogens instead. I have 4. 4 times 1 is 4. 4 hydrogens. And I have 2 over here. So to make it 4, I need to put a 2 in front. 2 times 2 gives me 4, right? So now I can do the oxygens. Now you have to take a look at all of them. So on this side I have 1 times 2. So I have 2 oxygens. And 2 times 1, I have another 2 oxygens. So in total, I have 4 oxygens. I need 4 on the side. What am I going to put in front if I already have 2 as a subscript? Well, 2 times 2 will give me 4. Or what I could have said is, I need 4. 4 divided by 2 gives me 2. Okay, so you can take your total divided by the subscript will tell you what you need to put in front. Now in this case it was a simple calculation. You really didn't need to think it through, but sometimes you do. So take your total divided by the subscript on the other side and it'll tell you which coefficient to put in front. Okay, so now I have 4 oxygens on each side and my equation is balanced. Let's take a look at the next one. Let me take a different color. Okay. So again, oxygen, oxygen, oxygen. So it's a similar reaction as you can see. It's another type of combustion. I know I told you not to pay attention to the fact that I said it's a combustion, but maybe you'll start noticing the similarities and recognizing combustions. So down the road when we talk about that, you'll already have that knowledge. Okay, so I have 2 carbons. I only have 1. So to make it equal, I'm going to put a 2 in front, okay? And this one, I'm going to keep it as 1. I have 6 hydrogens, so I'm going to do the oxygens at the end. So 6 times 1 is 6. I need 6 over here. 6 divided by 2 will give me 3. So I need to put a 3 in front, right? 3 times 2 gives me 6. Okay, how many oxygens do I have? 2 times 2 is 4. 3 times 1 is 3. So I have 7 oxygens in total. 7 divided by 2 gives me 7 over 2 or 3.5. Let me keep it as a fraction. 7 over 2. Now, I'm not allowed to keep fractions. We said we can only have whole numbers. What do we do now? So what do we do in math when we want to get rid of a fraction? Well, we multiply by, let's say in this case, this much, right? So I'm going to multiply by 2 to get rid of the half, essentially, the 2 at the denominator. But the thing is, just like in a recipe, if I double one ingredient, I need to double all the ingredients. So if I'm going to double the whole thing by 2, or I should say multiply the whole thing by 2 to get rid of this fraction, what do I obtain? I'm going to use, let's see, let me use, actually maybe I should go back to green. Okay, let me go back to green. So 2 times 1 would be 2. So my final coefficient would be a 2. Here, my final coefficient, this is going to disappear. My final coefficient would be a 7. Here, my final coefficient would be a 4. 2 times 2 is 4, and 2 times 3, final coefficient is a 6. So I would have 2C2H6, 7O2, 4CO2, and 6H2O after I multiply the whole equation. Okay, so this would be my final answer. So that's how you work it out when you have a fraction. Okay? All right, last one. So I said if you have polyatomic ions, start with those. You'll see it'll make your life easier. So here I have NH4 and I have PO4. I have NH4 and I have PO4. As you can see, most of the time, except for hydroxide, most of the time the polyatomic ions will stay as polyatomic ions. They will not break down. So if I balance my NH4s, I have one of them here. So think as if there's brackets, right? So NH4, I have only one. And here you can tell I have 3 times NH4. So if I have 3 times NH4, then I need to have 3 times NH4 over here as well. So I'm going to put as a coefficient, I'm going to put a 3 in front to make it equal. If I balance my PO4s, I have one of them here and I have one of them here. If I had more, I would have had brackets as I have over here. So I have one PO4, one PO4, so that will remain as 1 on each side to keep them equal. Okay, now do I do the hydrogens or the oxygens? Well, essentially they're present in all molecules, so it's really up to you to decide what you want to do. Essentially, you only have this coefficient to find. So let's count the hydrogens first. 3 times 4 is 7, plus another 3, right? Because it's 1 times 3. You're distributing this 3 everywhere. So 3 times 4, what am I saying, 7? 12. So 3 times 4 is 12, plus another 3, that's 15. Over here I have 1 times 3, so I have 3. So I have 18 in total. Now let's see here, I have 4 times 3 is 12. Now you have to do 4 times 3 times 1. Okay, had there been another coefficient here, it would have multiplied everything. So 4 times 3 is 12, times 1 is still 12. And I need in total 18. So I'm missing 6 over here. 6 divided by 2 gives me 3. Now, my equation is supposed to be balanced, but we will verify in this case using the oxygens. 1 times 3 is 3 for the oxygens. 4 times 1, so I need in total 7. I have 4 times 1, that's 4. And I have 3 times 1, that's 3. So I've just confirmed that my oxygens are balanced and that my whole equation therefore is balanced. Okay, so that's one way of confirming that you've done the correct work. If you have one more element to balance, but that essentially your equation is already fully balanced. You can use that as a verification method. And that's it for this lesson. Hopefully these 3 examples helped clarify matters. If you have questions, please don't hesitate to ask them. And otherwise, I will see you for your next lesson. And until then, take care of yourselves.